Hello everyone. So in this video, we discuss an abstract framework to answer a fundamental question we raised in the previous video. So the the question is about how the index change when we go from one function space to a subspace. So recall that the more index is associated with the second variation. And the second variation is basically about a symmetric operator. So you can think about it as a matrix in an infinite dimensional vector space. And the index is just the number of negative eigenvalues for this matrix. Now we reduce the matrix. We consider the matrix on a in a smaller function space, and we ask the question: what is the number of negative values for this matrix in the smaller function space? So that is the general um, question we are facing. So how do we answer that question? The key idea here is to somehow relate the reduction from a function space to a subspace with elements in that vector space. If we have a connection, then everything can be considered in the language of linear algebra, and then somehow we can figure out the exact relation. So how do we relate this reduction to some element in the vector space? Actually, the breakthrough idea is that we can interpret a constraint here, which is the reason for the reduction. We can interpret a constraint as a linear functional. So the appropriate language to consider a linear functional is the Hilbert space theorem. So let H here be a Hilbert space. Then a linear functional here, this can be considered as an element in the dual space of H star. But this H star here, it can be identified with H via the red representation theorem. So that's why the reduction can be related. The reduction can be related to some element in the space function that we are considering. So we have H here, Hilbert space. S here is a symmetric continuous bilinear form in this Hilbert space. H star is a continuous view of H. Now let phi here be an element in H star, and W here is the kernel of this linear functional. So certainly W here is a subspace H. So our goal is to track how the index change when we go from H to W. So we had to relate the more index of this operator S with respect to H versus the more index of the operator S with respect to W. And for simplicity, think about S here as a matrix. The more index is the number of negative eigenvalues. So when we have S as a matrix in some vector space H, we count the number of eigenvalues. Now we apply S to a subspace, then it also has certain eigenvalues, and then we count the number of eigenvalues uh, uh, for the subspace, and then we try to relate these two numbers together. So the main theorem that we prove is the main abstract theorem that we prove is the following. So it says that if the linear functional phi here is nice, and I'm going to explain what nice means a little bit later, then the more index with respect to W is equal to the more index with respect to H minus 1 if and only if the following condition is satisfied. There exists some element U in the Hilbert space H such that S of U dot here equal to phi, and furthermore phi of U is smaller than equal to 0. So this is the criteria so that the number of negative eigenvalues gonna be decreased by exactly 1. Otherwise, the number of negative eigenvalues stay the same. So this is a very satisfying answer under some assumption. So the assumption here is that phi is nice. So what exactly does that mean? So here we have the real representation theorem. H star, the dual space of H, can be equipped with an inner product so that it is isometric to H. Then we can, then the symmetric continuous operator S gonna induce a map S bar from H to S star by the natural definition S bar U. So remember, this is element is S star, which is the space of all continuous linear functional. So this is gonna act on some elements in H, and this is exactly equal to S of U with that element. So this is just the natural identification of a symmetric operator with a linear map from a Hilbert space to its dual. So the nice condition here means the following. So nice here means that phi here doesn't belong to the following set. This is so S bar is map from H to H star. So we can consider the range of this map. And if S bar here is not closed, so the range here is not closed, so we can close it using the induced metric, induced inner product, and then we just subtract the range of S bar. So in other words, nice here means that phi here is not a limit point in the pure limit point in the closure of the range of this map. So this map from one Hilbert space to another Hilbert space, you take the closure. So the closure here might contain some pure limit points if the map is not closed. So nice here means phi here is not a pure limit point. And this assumption is actually very might, because in application, the niceness here is normally verified via a Fredholm alternative. So Fredholm alternative is a statement about PDE, partial differential equation. So as we saw earlier, the second relation is associated with a symmetric bilinear form in a function space. So actually, this symmetric bilinear form is normally associated with some elliptic operator. That's why when we have some elliptic operator, then it is very, very natural to develop a Fredholm alternative for the associated PDE with that operator. And that's why the assumption here on phi is actually very, very mild, because it is actually just related to uh, the the presence of a Fredholm alternative, which is normally true when you have elliptic operator. So that is the abstract formulation that we developed, and this abstract formulation allows us to determine exactly how the index change when you go from one space to a subspace. We're not going to give a proof of this theorem, but we can say that the proof here is a functional analysis proof. We just use properties of the Hilbert space, the representation theorem, the inner product in this Hilbert space, and so on. So it's elementary proof, but it's also interesting. So how can we use this abstract formulation in practice? We're gonna illustrate an application of this abstract formulation to study capillary surfaces in the next video.